actually P1 times delta 1. So because of the P1, we have delta 1. So I draw it here. This is irregular shaped object. Let's say this is P1, this is P2. So for each of these external loads, we have corresponding deformation. So this is delta 2, this is delta 1 after deformation. And internally, we have the one that I showed you. We have this element. The original length is L. The change of the length is eta. We show it with eta. So this is eta. And the internal load which causes this deformation internally is shown by U. Similar to the text. So now, the work done by external loads is P1 times delta 1. Force times displacement. This is the definition of work or energy. And for P2 is P2 times delta 2. Force times displacement, the definition of energy or work. And then this is the work done by external forces. So I write it here, work of external forces. And work of internal forces, of course, is U times eta. Internally, we have U and we have eta. We will have more than one. So you have U1, you have U2. Corresponding to each of these internal forces, we have internal displacement. So we put sigma here. Sigma U times eta. So this is the concept that the textbook starts with. So we can write this equation provided the energy is conserved. That is the assumption. From here, the scientists started working on this formula, and the textbook doesn't show it, we don't need it. Eventually, they end up with the extensive formula. So I just write part of it here. That formula was delta I is integral m ei. Then I put 3 dots. And you know what formula I mean. That formula is derived from this assumption. So we conclude that if you want to use this extensive formula, then the assumption is the conservation of energy. We don't have waste of energy. Can you provide any example when the energy is not conserved from the high school physics? Or the energy is wasted?
All lost to heat?
Yes, loss of heat or friction. For example, I push this object from here to here, but it stops because of the friction, so the energy is wasted. So if you have friction in a system, part of the energy is wasted because of the friction. So this is the assumption here. And I just want to highlight some tips. The formula was delta I after shortening, integral m ei, and then we had sigma r bar k delta plus sigma m bar divided by k delta. So the last two terms are actually for torsional spring and linear spring. So this term is for linear spring. And this term is for torsional spring. And we discussed it. And it was a question from Race last time, something about R, what is R? So now, Race, do you remember what is R?
Rotational.
This is, no, rotation is for the torsional spring. So this is the force inside the linear spring, under the real load. Remember, we have two types of load, the real load and the virtual load. So the force inside, so I just draw it here. This is your linear spring. The force here, it is R. Okay. And then when you apply the virtual load in the absence of the real load, then the force here is shown by R bar. That's it. The same discussion when it comes to the torsional spring. This is a torsional spring. So we have, under the real load, you have a moment here, we show it with M. The moment inside your torsional spring. Under the virtual load, you have another moment here, we show it with M bar. That's it. Now, I have a reason for discussing this. It is about the sign. R and R bar, M and M bar. When are they positive, when they are negative? To avoid any confusion, is there anybody who can help for this? This is the force in linear spring. So you know that the force is negative when it is in compression. So I just say it is in compression, then it is negative. If it is, can you see this color? No, right? So because the background is dark, so this is blue, so blue cannot be seen. So now, another one is tangent. And you already know why compression is negative, why tangent is positive. You already know that, right? So the same rule applies for R bar. If it is in compression, it is negative. If it is in tangent, it is positive. So you already know the sign. If both of them, now I want to conclude. Is there any question, Clement? Here. Now I want to conclude. If both of them, are in compression, then their multiplication is positive because both of them are negative. If both of them, so I say multiplication of both of them is positive because negative times negative. If both of them are in tangent, again, the multiplication is positive because one of them is positive, the other one is positive. If one of them is tangent, one of them is compression, the multiplication is negative. And you may say that, okay, we know that, but it may confuse you. That's why I'm highlighting it. Okay? So if one of these two forces is in compression, the other one is in tangent, the multiplication must be negative. In other words, if they have the same direction, if both in compression or both in tangent, the multiplication is positive. So the same concept comes here. Who can help? Raymond. Now we are going to discuss this in the same manner, but this is moment, this was force. So can you explain?
So it's going to be whether it rotates clockwise or counterclockwise?
Yes. So it means that if both of them are clockwise, they have the same direction, so the result is positive. If both of them are counterclockwise, again, because they have the same direction, the result is positive. So if they have different direction, one of them is clockwise, the other one is counterclockwise, the result is negative. That's it. So it will help you, because sometimes if you just want to follow the mathematical sign, then it will be a bit confusing. The software works based on the mathematical sign. One of them is positive, one of them. It's just based on the algebraic computation. But you are human, so you can think better, make it easier for yourself in the exam. They have the same direction. The multiplication is positive. They have different direction. One of them is clockwise, the other one is counterclockwise. The multiplication is negative. It's easier. Okay. Now, remember in the previous example, in previous class, we applied a unit load on this structure. That unit load is the virtual load. Do you remember that? You have it on your note. If you look at your note, we applied a unit load. And the reason we applied a unit load was because if you look at your note, we wanted to calculate. Okay, this is the problem that we solved in previous class. This one. This was point B, this one point A. The length of the beam is L, the rigidity is EI. And then the question asks you to find the displacement of point B. So basically, delta B Y was the question. Clement, how do you apply the unit virtual load? Where?
Point B,
How? Horizontal or vertical?
it's Y, so vertical.
Yes.
Up, down,
Then Y, yeah, so it's vertical. Clement said because it's Y, so we apply it vertically. But downward or upward?
Doesn't matter, I guess.
It doesn't matter, yes. But why? Because you assume it is downward. Clement said it doesn't matter, yes. So you apply downward. At the end, you find delta By with its sign. If it is positive, it means your assumption was correct. If it is negative, it means it is inconsistent with your assumption and you have to flip your assumption. It means delta By would be upward. So now, by drawing unit load downward, you assume delta By is downward. You assume. But later, if it is negative, it means you have to flip the sign. It is upward, right? So it goes for any other directions. And this is important. Any question for this? Now, looking at this formula, it seems not difficult, but basically, structure analysis, keep it confidential. Structure analysis is the most difficult course of civil engineering. It is the most difficult. But it still depends how the professor set the level of difficulty. But during my generation, this was the scary course. The reason is that it has a lot of details, and the textbook doesn't discuss those details. So it's not your fault. So now, still after a lot of editions, I don't know why the textbook doesn't include those tricks. I will let you know about them. For example, do you remember in first line, it has a lot of tricks. But the textbook doesn't include all of them. When it comes to statics and dynamic, yes, they are good. The textbook is good. 95% or maybe 99% of the tricks are already included in the textbook. But for structure analysis, not yet. So let's look at the tricks for delta I. It is about how do you apply this unit load. So we have a comprehensive example, and then in this example, we just look into the direction of that unit load only. We don't go through this formula. We just want to practice that. So this is the structure. It is a frame. There is an internal pin here. Roller here. shear hinge, and roller. Points A, B, C, D, E, F. Now, if you want to write the question, this is the question if you want to write. Show the unit load required in virtual work for the given displacements for the structure in below. For the given displacement for the structure in below. Now, number one. Let's say you want to use this formula and the question is asking you to, number one, horizontal displacement of B. Horizontal Okay, Clement, how do you apply a unit load if you want to use this formula and then you want to find the horizontal displacement of point B?
So cut out B and then horizontal, if you remove horizontal, it would be just a,
So it's just horizontal. So you apply a unit load at point B, as you said, horizontally.
oh,
Yes?
yeah.
So then, what color? Is it from right to left or from left to right?
Doesn't say.
Doesn't matter, as Clement already discussed, right? So you assume, for example, it is from left to right or right to left. At the end, you find delta x for B. If it is positive, your assumption is correct. If not, you flip it, right? So this is the answer for section A. No issue. Section 2. So we are just practicing how to place the unit load only. Vertical displacement. Vertical displacement of point C. Then someone who are, no, what do you think? Where do you place it? The unit load.
Right is, I think, right to the left of C.
Left of C. Okay, let's. So I erase the answer for the first part. I don't know how you want to take a note of it because I don't want to redraw it. So now we are done with section 1. And Nono said vertical displacement of C. Nono said at the left side. Why? Basically, when it comes to an internal pin, it doesn't matter. You place it right on the axis of the pin. It means when you want to analyze this structure, you can place it at the left or at the right. You will get the same answer. So now, you place it right at the axis of the C. Okay. But later when you analyze this structure, you have to take, you have to disassemble it and take different pieces of the structure apart. Then you say, okay, where to put the unit load? It is up to you to put it at the left side or the right. One of either. You will get the same answer. Okay, so this is actually a question that I discussed in statics course. And I told you if you pass static with me. Okay, so this is the answer for second one. So it doesn't matter left or right. Next part. Next one. By the way, if I ask you a question and you cannot answer, it is fine. This is just a way to get you involved in the class. So it doesn't matter if you cannot answer, it's fine. Third one, slope or rotation. So I write rotation. Rotation. Inside the parentheses, I write slope. because the textbook is using the terminology slope at point E. At point E. So, remember inference line? In the inference line, it was about slope, and slope was tangent of theta, right? In the inference line. Slope was tangent of theta. So when it comes to inference line, it is tangent of theta. When it comes to virtual work, it is the rotation. It is theta, not tangent of theta. So write it on your notes so you won't can. When it comes to inference line, it is, when we say slope, it means tangent of theta. In this concept, when we say slope, it means theta itself. So if you go to different textbooks, they say rotation, slope. Our textbook says, it says rotation, slope rotation, something like that. So now you know what it is. So basically, we are looking for theta at point E. That's it. So you call it slope or rotation itself. And the unit is radian. So previously we were looking for delta x, delta for point Bx. And then we were looking for vertical delta for point Cy. Now we are here. So now you understand the meaning of slope, rotation, whatever. It is theta itself. Then, because it is a bit difficult, I asked Alex. Alex, how do you apply a unit load for theta at point E? This is rotation. So when it is rotation, it means it is not a force. It must be a moment, right? Because it has something to do with rotation. So we apply a unit moment, not a unit force. And of course at point E. So this is the answer. So I erased the previous one to avoid any confusion. Point E. Now my question from Alex is what is the unit for this? Newton meter. It depends. Keep, foot, whatever. The amount is one. My question is why did I draw it clockwise? Why not counterclockwise?
Doesn't matter.
Isn't it just sign convention?
It doesn't matter. Yes. It doesn't matter. So you assume it is counterclockwise or clockwise. At the end, once you find theta E, if it is positive, it means your assumption is correct. If it is negative, it means the rotation is inverse. That's it. This one is also written in the textbook somewhere. Okay. Next. Basically, you will not face some of these items in this list, but I have to tell you. I don't know, maybe you go to another textbook and you face one of them, so you should know all of them. Slope at left side of C. So I write rotation at left side of C. Okay, what does it mean when we say rotation? So I need to clarify the meaning of theta. So I'm going to erase this part. We don't need this part, so I just erase them. Theta is the angle from the horizontal axis. So if this is x, and you draw a tangent line on the deflection shape of your structure, that point will form an angle with x. This is theta. So it could be in this way. when you draw that tangent line, the angle could be more than 180. So what is this dashed line? This is tangent line. The tangent line drawn to the point on the deflection shape of the structure. So if this is the deflection shape of your structure, for example, and you want to look at point A, and you want to draw theta for point A, you draw a tangent line at point A from calculus, you know how to draw it, and then this tangent line will form an angle with x-axis. That is theta. Now, because we need this concept later, I change the name of point from A to C. I want to call it C. So this is the tangent line for point C. If I just move a little backward, somewhere before point C, I come here, a little backward. It means at the left side of C, and I draw a tangent line. That line will form an angle. This is theta, C left. I know you cannot see that. So I read it for you because I'm sure you cannot. This is theta C, okay. This is theta C left because it's left side. In statics class, one of the students said that I cannot see because they are very small in font. So I read it for you. Now I'm going to, any question for this? Can you see that? Now we repeat this process for the right side of C, a little after point C. I use orange. So after point C, for example, here, I draw